Right, so pre-calculus 20, here we are using McGraw-Hill Ryerson pre-calculus 11 textbook, as you have in front of you. This is on page something or other, unit 4, 400 and some, 420, right on, thank you, 420. So we're talking about systems of equations and inequalities. Systems of equations and inequalities. Systems, first of all, that means more than one thing. And in this math, you've already done this. I think if you've taken Foundations 20, you've done this already. How many of you have taken Foundations 20 math? FM 20? Yeah. Okay, most of you should have. This is pre-calculus 20, so probably most of you should have done that. But when we have lines or curves and lines and curves, when we have more than one sort of like function graphed at the same time, if each one of those graphs represents something, we can gain a lot of information from plotting them all in the same graph at the same time. And that's what a system of equations is. Now, inequalities, later in the chapter, we're going to talk about inequalities, which again, you studied in Foundations 20, where we have a line and everything, all the points above that line may fit the inequality, less than or equal to, or greater than or equal to, or whatever. So those are the inequalities that you studied in Foundations 20. Some of you maybe enjoyed that, some of you didn't. Anyways, we'll hit it again here, and hopefully everyone will find some success this time. So I'll let you read just sort of the introduction a little bit here. There's a lot of science and nanotechnology that's related to systems of equations. Calculus is based on systems of equations when we're talking about maximizing or minimizing things, or we're talking about calculating displacement, movement of particles, or things like that. We talk about systems of inequalities a little bit. And so when you get to calculus, we're going to talk about working with that a little bit, but we're going to use calculus techniques. So now we're just kind of studying the big concept using regular algebra techniques. But this is pre-calculus, so I try and inform you of what's ahead when I can. Okay, chapter 8, now looking at 8.1, very quickly here, systems of equations. I won't go through too much of this. This is pretty interesting. There's this nanotechnology here. These little microchips are so small, embedded in a person's finger, that sort of thing. That's a little scary. But anyways, of what can happen at such a small level, right? So anyways, so this is an example. Now this is there's 1, 2, 3, 4, 4 equations here plotted on the same graph. I'm not going to spend a whole lot of time on what the textbook, does on this example, but this is an example where if you graph certain relationships and you have a number of relationships that you can see at the same time, you can make a really good decision, whether it's a business decision or a medical decision or something to do with sports and all this sort of. If you can combine several factors and find out where this factor is a minimum or where this factor is a maximum, if you can kind of juggle that around and find a sweet spot, then that's going to be very helpful. And that's the essence of what we're learning. So again, I won't get into this too much because I don't even fully understand this myself, but I mean, all of these things represent something different. So marginal cost, total average cost, okay? So if we're talking about what it costs to make something, there's going to be a graph. It's going to cost a lot if you make a little. If you buy bulk, this orange here, right? If you buy bulk, you're going to get cheaper parts. If you have some kind of assembly line, it's going to go quicker. So the cost overall is going to go down. What about the demand? Well, if you make a few, not very many of these things, the demand, this red line, will be high. Okay? There's not very many out there, so the people that want them are clamoring for the few that you make. If you make too many, the demand is low, and you're going to not be able to charge as much. See, the price will be low. So those are two things. Revenue is what you make, right? So again, this is the blue line. If you make a very few, you can charge a lot and make a lot. If you make too many, the price goes down. Blah blah blah. So taking all this into account, you can see that the cost is relatively low, the demand is still relatively high, The revenue is kind of creeping up there. It's not too low. So you can look at this, and at this 600, do you see where there's two graphs, and I'll zoom in a little bit. Two graphs intersect here. This graph right here, the demand is still pretty high. The average cost is pretty low, close to its minimum, and so on. The revenue is a little bit low, but you can't really do anything up here because the cost is so high and blah, blah, blah. So this is kind of a sweet spot, this sort of 600 units of things. And with these graphs, you can kind of figure out how much of something you want to make to maximize your overall profit, let's say, okay? So I don't know if that helps you understand why we're studying this. And again, that's a complicated example. But this is something now that you'll have to kind of learn to remember. So we talked about a system and what that is. It's two or more equations. And if you have a system of linear-quadratic equations, that would mean one function is a straight line and the other function is some kind of parabola. Okay, linear quadratic. And as we focus in on the different options for a linear quadratic, you can have a system where there is no point of intersection. So that means for this system there is no solution because the intersection point or points will be possible solutions for these. Now, when two lines intersect, that intersection point is important. They both have the same x and y values. So if you're trying to solve a system of equations, you're trying to find a point or points that are common to both graphs. Very important. This system has one solution because there's one intersection point. This system right here has two solutions. And this is the max number of solutions that you can have for this type. Okay, because if you draw this line any which way, it'll only it'll only cross a maximum of 2 times. Okay? So you need to be able to visualize this and understand that you could have 0, 1, or 2 solutions here. For a system where 2 quadratics are employed, you could have 0 solutions again. You have 2 parabolas that don't intersect. You could have 2 parabolas that intersect at 1 point and 2 parabolas that intersect at 2 points. So for both of these types of systems, we have a maximum of 2 solutions. Okay? And that's for linear and quadratic. So just a couple notes here as we've talked about. Any ordered pair, so that is any point x, y, that satisfies both equations in any kind of system, linear quadratic or linear or quadratic, is a solution to the system. So a point that satisfies both equations, or graphically, if you think about it as a graph, the points where they intersect, wherever they cross, those are solutions to that system. Okay? So again, hopefully this is bringing back some memories from Foundations 20, and hopefully you're remembering some of this. So they could have no real solution, 1 real solution, or 2. And it's the same for both of those types. Okay, any questions about that right now? Any questions? Okay. System, 2 or more, straight lines or parabolas, that's what we're dealing with. 0, 1, or 2 possible solutions. And the solutions are the intersection points. All right, so this question now says, I think I'm zoomed in a bit. This question says, solve a system of linear quadratic equations graphically. So what I'm going to do is I'm going to take a moment to, you're going to get your graphing calculators out, and we're going to go over this using graphing calculator. Okay, so on your calculators now, if you got the, please hit Y equals button, and you get this screen. If you have anything on there, please clear everything away. So hit clear, and they should be cleared. If your plots are on, like this, if that's highlighted, that's bad. Okay, this should not be on, this should be off. Now, we're going to use a graphing calculator in a moment, but we have to look at this question. You don't have one? No. Okay, just share with the neighbor for now, please. You guys share one. Solve the following system. Okay, graphically. So what we're going to do is we're going to graph each of these. The only problem is that your calculator can only graph an explicit function. That means that we need to isolate for y first. Okay, So you're going to have to do this most of the time with these questions if y is not already isolated. So that's easy. What you do is you get y positive and by itself on one side, and that's really easily done by taking this negative y and you add y to both sides. So we're going to get y equals 4x plus 3 because these stay on one side and the y goes to the other side. Look good? The second one, again, I'm going to bring this negative y and I'm going to add y to both sides. So this is going to be y equals, what's left on this side? 2x squared plus 8x plus 3. You guys okay with that? So now that we have these in the form that we want, we can now use the graphing calculator. Just be thankful that you don't have to graph all this by hand all the time, okay? You know, table of values, plug in some points, draw your lines, sketch it out. We're going to use the graphing calculators to help us out. So let's get that graphing calculator back up. And we will input the first equation in. So that's going to be 4x plus 3. 4x plus 3. Just simply like that. We'll go down to the next line and we'll type in this quadratic. Note that this is a straight line, the first one. Second one is a quadratic. So 2x squared plus 8x plus 3. Okay, you guys all right with that? Everybody see that? Okay, and then you hit graph. And if you need to, if the origin is not right in the middle of the screen, hit zoom 6, and then you should get this looking like this. Okay? So does everyone have a graph that looks somewhat like this on your graphing calculator? Anybody not getting this for some reason? Again, here's the equations you should put in. All right? And this is what your graph should look like. Okay. So it appears, it's a bit tricky to see, but you can clearly see we have one solution here. So this point's going to have a negative x value. It looks close to negative, what is that? Negative 1, 2, and down maybe 4 or 5. Okay, so intersection point here, and it looks like there's going to be an intersection point there. Okay, so how do we find intersection point again on a calculator? You should know this, I think, but hit second function trace, that's the calculate menu. We're going to go down to number 5, hit number 5 for intersect. Now, the cursor is going to be on one of the graphs. In this case, it's the straight line first. And it's going to ask you first curve, you're going to say yes. It's then going to pop over to the second curve, you're going to enter, say yes. Now, the guess, okay, move your cursor close to the intersection point that you're wanting, because there's two. So let's move it closer to the one near the bottom. And then when you hit enter again, it should calculate the intersection point at negative 2, 5. Okay, so negative 2, 5. That's one of them. And we're going to verify that in a second, but let's calculate the other one real quick. So in the same manner, second function trace, number 5. You can hit number 5 or scroll down to 5 and hit enter. It's going to ask for the first curve, and you can just look up here and say, yeah, that's the first one. If you can't see exactly where the cursor is, say, yeah, that's the second one. Now, you're going to move your cursor so it's closer to the other intersection point, over here somewhere. And you're going to hit, it's going to say guess, and you're going to say yes, please, and it's going to say, here's your intersection point over here. The cursor will blink there, and it'll say 0, 3. Okay, so 0, 3. Now, it appears that those are the solutions to the equations. Graphically, it appears that those are good. We need to verify, so let's check both solutions and to make sure that they make the equations true for both. So 5 is y and negative 2 is x. So let's make sure this one's good, and we'll make sure that 5 here is good for the other one as well. Okay, so a slight correction there. I didn't write down the negative, so negative 5 is the y value there. So this one checks out for both equations, and then you do the same thing for 0 and 3 and make sure that checks out, and we'll do that as well. Okay, so yeah, you would just show your checks there. Just for sake of time, I won't do that right now, but show your checks, and these do check out, so those are the solutions. Okay, any questions about that now? Good with that? All right, so take a moment if you have your calculator or if you have some graphing technology to check this out. Here's your chance to just give this one a try. So here's what your system should look like, and these are your intersection points. Now I did this on decimals.com, so you can certainly feel free to do that at home. It's a nice way to do that. But for the tests and stuff, you'll have to be able to use your graphing calculators to calculate intersection points. So anyways, if you're having trouble with that, let me know, and I can give you a little bit of a hand with that. I want to do our last example, though, before we move on. It's the last example I want to show you and work with you on, okay? So I can come back to that if you're having trouble with that graphing part. So example 5 says this: model a situation using a system of equations. So suppose that in one stunt, 2 Cirque du Soleil performers are launched toward each other from 2 slightly offset seesaws. So there's these 2 performers are standing here, and they are launched towards each other, okay? Like they're going to like meet somewhere. The first performer is launched, and 1 second later, the second performer is launched. So we have one performer is launched, and then a second later, the other one is launched. So they kind of like, kind of meet at different points like this, right? One's maybe going up and one's coming down by that time. They both perform a flip and give each other a high five in the air. Each performer is in the air for 2 seconds. The height above the seesaw versus time for each performer during the stunt is approximated by a parabola as shown. So the first performer leaves at time 0 and spends 2 seconds in the air. The second performer leaves at time 1 second and also spends 2 seconds in the air and in a similar jump. So we have this graph, and they actually give you this graph, so that's great. They also tell you that the maximum displacement there is 5 meters, looks like. So that's why it goes up as high as 5 on the y-axis. So given this graph, it looks like we have an intersection point right there. Now this is important because we're going to be able to figure out some information from this graph. So what does it ask us to do? Determine the system of equations that model a performer's height. Okay, so come up with the equations that are graphed here. We can do that. Solve the system of equations graphically using technology, and interpret your solution with respect to the situation. So coming up with the functions. So we have to remember how to do that. Okay? So we have to reach back into chapters that we've already done, okay? Because we've already learned this. You might be a bit fuzzy on it. But one thing you can know here for this blue one, and I'll use the kind of same color, this blue one is we have a vertex. The vertex is 1, 5. So do you remember how we determine an equation for a quadratic given the vertex? We use the vertex form, right? Do you remember that? Vertex form for an equation. And so what is that? That's going to be y equals a times x minus p squared plus q. Does that ring a bell? So what we need for that is we need the vertex, pq, which we have, and we need a, which we can solve by inputting a point here, okay, and to solve for a. So there's 2 parts, and I'll do that with you, okay. So what we need to do is we need to say, all right, y equals a times x minus 1 squared plus 5. Okay, you know that. We're not done because we need to find out what a is, and so we're going to put a point that we know is on this graph, like 0, 0. That's 1. We're going to put 0 and 0 into this equation for x and y. And I'll change to a darker blue so that those of you in the back can see. And then we solve for a here. So we have 0 equals a times, well, that's negative 1 squared. Well, that's just 1a plus 5. So a equals negative 5. Does that make sense? Now we can piece this with the proper a now, and we can come up with our function. So we have y equals negative 5 x minus 1 squared plus 5. Looks to be the case there. Okay? And then we do the same thing for b. Use this vertex of 2, 5 and a point of 1, 0. You can choose that one, solve for your a, put it all together. All right, so in doing that, you should get, for this one, would be y equals negative 5t minus 2 squared plus 5. That's what you would get. Okay, now in this actual graph, we have h and t, not x and y, we have t and h. And so really what you could do to be a little bit more accurate to this graph here would be to write it like this. H is the height, okay, and it would look something like this, sorry, and the x would be the t. Okay, so that's what you could do there. That would be the right answer there. For A. Okay, solve the system graphically using technology. You could put each of these, and you're going to want to use x and y probably for your graphing calculator. Find the intersection point right here. Okay, that intersection point there. And again, I'll save you the time just as I explain this. You would put those in, and for, so that's not B. For B, you would get an intersection point of 1.5 and 3.75. You could maybe get that from the graph, but it's not very exact if you just look at that graph. So using your graphing calculator would be perfect. And then C, this is really important. This is one of the big reasons why I wanted to do this example. Interpret the solution. Okay? So again, if you think about the situation, we have two performers that are jumping towards each other. One jumps, and then the other jumps a little bit later, and they're going to meet somewhere at a certain height, and they're going to meet sometime at a certain time. And this intersection point tells us the time after the first one jumps that they will meet, and it also gives us the exact height in the air that both of them will be at the same height at the same time. So same height, same time. So 1.5 seconds after the first jumper, okay, after the first jump, the two will meet at 3.75, what's the units? Meters in the air. Okay, sorry, that's pretty messy there, but okay, so interpreting this intersection point too is really important, okay? We're going to have to look at it that way. All right, any questions with that? You can take a moment to look at the key ideas for this lesson. These are things that we've talked about already. Oh, I should mention one more important thing though. Everyone's attention. One more important thing that, this one right here. Okay, this right here I have to highlight. I didn't highlight that before. If you have two parabolas, guys, if you have two parabolas, let me just show you this, different example. But if you have two parabolas, so if you have a parabola and a parabola, you could have two solutions, 0 or 1, we know that. But if you have two parabolas that exactly map onto each other, and they're the exact same parabola, that's an infinite number of solutions. That means that every point on both graphs is a solution. Okay? So that's the one I didn't highlight before, but you could have an infinite number of solutions if the two parabolas are the exact same. Or if the two lines, although we're not doing double linear, I don't think we are linear, but two lines, if you have two of the exact same lines, an infinite number of solutions there. Okay? So just a note there. Okay? So that's your key ideas. And your assignment for this 8.1, why don't you do number 1 to 4 and number 10. 1 to 4 and number 10. Again, that would be the minimum recommendation there for your homework. And that will look something like this.